Welcome back to Wood Engineering. I'm Jeff Rochko from Carleton University, and in this video we are going to continue with part 2 of our epic dive into beam column design examples. So we are continuing this example, and so far all that we've done is we have assessed basically what is a reasonable amount of eccentricity to assume, and that is basically we have just gone through and decided how big is reasonable for this value here, and that value depends on what is going to be the depth of my member. The larger the depth of the member, the larger the eccentricity is going to be, which is going to change the applied moments that are caused by that eccentricity acting on the vertical loads, because we have a moment that's equal to the vertical load P times the eccentricity E. So we kind of picked an upper bound size for our column, our beam column here, which was somewhere around 400, and we are very confident that the design that we're going to end up with is going to be less than 400. And we found through geometry that the E is going to be 0.1 of the depth of the total depth of the member. And so if we are confident that our member is going to be less than 400 millimeters, then we can be confident as well that our E is going to be 40 millimeters or less. Okay, so now that we have that, we can go through and do all of our load calculations and load combinations, which is what this video is going to be all about. And we have a pretty complicated situation here for load combinations because, again, we have moments coming from the lateral loads, we have moments coming from the vertical loads plus times the eccentricity. We have shear coming from those lateral loads, and we also have the fact that the wind acts as an uplift. So whereas in the previous video, all the calculations were very quick and dirty, was making a ton of assumptions just to get that upper bound size value. I probably would have gone even quicker if not for trying to explain all of those assumptions. I mean, the idea was just to get something that is just very rough. This is kind of our upper bound size and our upper bound eccentricity. So now we're going to do it more very much, in fact, with a fine-tooth comb. And we're going to really determine exactly what those loads are going to be for all of the load combinations. So this is a pretty big task for this problem to do it by hand. Okay, so you'll recall that we have our dead load is 150 kilonewtons. These are all the specified loads, right? The unfactored loads. Our snow load is 200 kilonewtons. By the way, here our long-term loads are not greater than our standard term loads, so we don't have to use the interpolation for KD. We're just going to use the regular KD values from the table. And our wind load from uplift is 100 kilonewtons, but upwards, whereas the others were downwards. Okay, so now what I'm going to do is I'm going to draw all of the shear and moment diagrams for all of these, and it's, they're very simple loadings, so the shear moment diagrams are not very complicated. Let's start with the dead end snow loads, and these ones all act downward. These both act downwards. Dead end snow, they both act downwards, so they both basically do the same thing. So this is what my my diagram looks like if I draw my my model of what this looks like. Okay, so we have a pin at the bottom. I have a kind of vertical roller at the top. And my dead and snow act to the right of the column, right? So if I go back up here, they act to the right of the center line of the column. They're on this side. Okay, so since they act to the right of the column, I'm going to get a certain bending in a certain direction. And so this is going to be my dead load is 150 kilonewtons and my snow load equals 200 kilonewtons. And I have an eccentricity here. And that eccentricity equals 40 millimeters is what I'm assuming based on the previous analysis. Okay. So if I do that, now I can draw my axial, shear, and moment diagrams. So my axial, I'll draw it over here, is going to look like this. Okay, so I have a compression load, and that compression load is constant. I'm going to say compression, just to make that clear. And the value here is going to be 150 for dead and 200 for snow. And so I'm going to make those numbers negative. I'm going to consider that compressive loads are negative loads, just to make it a bit easier for me to keep track. Equals negative 200. Okay, and these are in kilonewtons. Okay, let's draw shear. Shear diagram is easy. Looks like that. There's no shear on this beam, on this beam column caused by those loads. And last, the moment. Okay, so remember my reaction is coming straight here. There's no eccentricity on the reaction. So there's no applied moment at the base. Basically, this system is a beam column with what is effectively a moment at the top, and that moment is so let's draw it. This is what my free body diagram looks like. Actually, if I'm drawing the free body diagram, I won't draw that. My effective free body diagram looks like this, right? This is dl times E and SL times E. Oh, I made a mistake in my analysis. Huh. Okay, no, it turns out there is a shear. Now that I'm drawing the free body diagram, I notice that my notes are wrong. So there has to be a shear here, because this is basically, I have a vertical load. So let's call this P instead of DL and SL. So let's call that P times E. That's my moment. This is P, this is P. And then I have to have a shear to balance that moment, right? So it's PE. P times E is my moment. So I have to have a shear here that is P times E divided by H, right? And same down here in order to resist that moment. So I do need a couple here, PE divided by H. Okay, so that means here I need to have a shear. That's PE divided by H. Okay, let's figure out PE first. Whoops. Let's figure out PE first. So here's my moment diagram. And my moment diagram is, and the value of this is PE. So that means here it's going to be 150 times 0.04. So remember that E equals 0.04 meters. So up here, my PE is going to be equal to, dead load is going to be positive 6 kilonewton meters, and snow load is going to be positive 8 kilonewton meters. Okay, and then for reasons that are going to become clear in a little bit, I need to also find here and here, which are the 1/3 points. Okay, so that's my moment diagram. Now for PE divided by H, it's going to be basically 6 divided by 3 is going to be 2. So for dead load, this is going to equal 2 kilonewtons. And for snow load, this is going to be P times E is 8. And it's going to be 8 divided by 3. 2.67 kilonewtons. Okay, so now I have my moment, my shear, and my axial. Good thing I noticed that shear. Okay, so that's it for the dead and snow loads. So now I have my moment, which is the important bit, and my shear, and of course my axial load. So now let's go and do the same thing for the wind load. And we also need to keep track of which direction the bending is. So if I look up here for this one, basically it's concave right, the bending, right? So that means that it's bending like this. Okay, so that's where the side where the positive moment is on. Okay, so now let's look down here at the wind load. Okay, I'm going to draw my diagram again. Then we'll be careful doing the free body diagram. Okay, I have this. I have a pin at the top, roller, and then I have my lateral loads. Okay, so this time I have a very similar situation, except I have the added 30 kilonewton loads pushing sideways. And my wind load, instead of pushing down, is pulling up. So it means it's going to bend things in the opposite direction. So let's start with the axial load. The axial load bit is very easy because it is just 100 kilonewtons in tension. Okay, and if I look at my free body diagram again, I'm going to still have a shear. So if I'm going to split this. Okay, since I can apply superposition, since I'm doing a linear analysis, I'm going to split it into what is the effect of just the vertical load and what is the effect of just the horizontal loads. And then I'll combine them together after. So just like before, I have a shear, which is caused by the application of that moment at the top. And so the loads are like this. Okay, and from the moment, and then the moment looks like this. Okay, the bending is now this way, so it's concave left. Okay, so the bending is in the opposite direction. And this is the load times the eccentricity, right? 100 times E. I should write that this is the moment, kilonewton meters. And 100 times E is basically... Okay, that's what the moment is going to look like. So again, those points are the third points. We're going to see exactly why that's the case in a second. So let's look at the horizontal loads now. Just from horizontal. So you can solve this on your own. It's just 2-point loads on a beam. And the shear looks like this. And this is 30, and this is 30. Again, these are all unfactored loads because we're going to factor them after when we look at our load combinations. And then the moment, and that bending direction is the same as the bending direction caused by the uplift. Okay, so I have my column like this. I'm pulling it on this side, pulling it up, which is going to make it bend this way. Okay. And at the same time, I'm assigning some lateral loads that are going like this, which are also bending it in the same direction. Okay, and the value of these moments is 30. And this also bends like this. Okay, so you can see why I put the 1/3 points there, because that's where I have the maximum moment, right? This here. This is our 1 meter, 1 meter, 1 meter. So those are our third points. So because I want to know what is the moment at the third point and what is the moment at the top, because those are the points that are going to govern this design. Those are where the highest potential moments are going to be. So now that I have both of these, I can come back and calculate the total for wind by superimposing both of these moment diagrams. Okay, and there's the full moment diagram. I just did that by adding up the moments at each of those 1/3 points. Or likewise, I could have done it by integrating the shear by calculating the areas of the shear diagram. Okay, so that's my total wind diagram for this beam. Pretty complex, went through the whole thing. So now we have some values that we can use in our design for moment and axial load. Okay, so let's summarize those now. We're continuing with load combinations. Okay, so the axial loads were, as we already said, okay, so those are all the maximum shear loads. And those are all happening at the ends of the members. So that is going to certainly be the shear load that we want to compare to our shear resistance at the compression side notch. And our moments, we're going to look at in two locations. One is what's the moment happening at the top, okay, here, because for wind, that's not the maximum, but for my dead and live, that is the location of the maximum. So we're not sure which one is going to govern starting off. So I'm going to look at moments at the top. And the second one I'm going to look at is at this point here. So this is the maximum moment for the wind. It's not the maximum moment for the dead and snow, but it still has some moment. So we are going to look at both of those cases separately. So there are two possible places that could govern, depending on the relative value of them and what load combination we're talking about, obviously. So for top, we have dead load is 6 kilonewton meters. Snow load is 8 kilonewton meters. And I'm going to call those ones, shall we call those positive or negative? Let's call those positive because they're on the right side of the moment diagram. We'll call that positive and positive. So same with the axial loads, I'm going to call those ones positive and this one negative. And the wind load is going to be -4 because it is on the left side of the moment diagram. So this is just how I'm going to keep track. Of course, the beam itself is balanced, so it doesn't care which way the load is being applied, but when I sum two loads, they are going to add up arithmetically, right? So the -4 wind load is going to reduce the total load if it's added to the effect of the snow load, because they want to bend it in the opposite direction of each other. Okay, and for the bottom, sorry, not the bottom, we're talking about 1 meter down. Okay, so obviously the wind load is the one that's causing the most bending. So probably that negative bending case is going to govern. But, you know, so I'm assuming that you're going to do this in a computer or something, spreadsheet. So I'm going to go through all of the load combinations explicitly. Okay, and shear we have done. Okay, great. So now we have all of the different load cases for all of the different places that we want to consider. So we want to consider axial load in the column. We want to, like the load combination for axial load in the column, we want to consider load combination for the shear, and we want to consider load combination for the moments at two different locations, the top and 1/3 of the way down. Now it's really looking like the moment at the 1/3 of the way down is going to be the one that governs. But in the interest of completeness, I'm going to consider both of them separately. Okay. So I'm going to go through each load case. At some point, I'm just going to speed through it. I'll do the first few manually. And I'm going to also make sure to identify what is the KD, the duration factor that's associated with each load case, because we're going to need that information later. Okay, so where am I getting these load cases? Again, I'm going back to the standard. These load cases actually, you know, in the 2019 version of the standard, it just refers to the National Building Code. So it doesn't actually give these tables. But if you have the 2014 version of the standard, it has the table. And so these are the load combinations that I'm considering. So I'm doing this one here, dead. This one's easy. This one, now, in some cases, I'm going to have to consider this 0.9 dead, right? Because, especially for this one, because the wind is acting in the opposite direction of the dead, right? And then I'm also going to compare each of these load combinations with or without companion loads. Okay, so there are tons of, there's not just 5 combinations I'm going to check it's going to be more like, let me see, 1, 2, 3, 4, 5, 6, 7. There's about 8 here that I'm going to check. I'm going to leave out load combination 2 because we don't have live load, so that one's not going to govern. Okay, so I'm basically doing 1, 3, and 4. 5, I don't have any earthquake load, so that one's not going to govern. So I'm basically doing 1, 3, and 4, and with and without companion loads, and with or without the 1.25D versus 0.9D. Okay, so that's the general approach that we're taking. So let's start with load case 1. And load case 1 is only going to have dead, so the KD is equal to 0.65. Okay, so my PF for this load case is 1.4 times P dead, and that is going to equal 210 kilonewtons. So it's basically 150 times 1.4, and I get 210. Okay, then my shear, my VF for this load case is going to be 1.4 times my shear, which is 2.0 kilonewtons. Which is 2.8 kilonewtons. And my moment is going to be 1.4 times MDL at the top. Okay, so that's 1.4 times, I'm just taking which one's the maximum here, right? So moment is maximum for dead load in the top of the column. And since I only have dead load, there's no point considering the other one. So I get 1.4 times 6, and that is 8.4 kilonewton meters. And at the top is where that's happening. Okay, so I mentioned I'm going to skip load case number 2. So let's move on to load case number 3. I'm going to call this one load case 3A. And this is basically dead plus snow plus live or wind. So this one I'm going to do just the dead plus the snow. So this is KD is going to be 1.0. Okay, I'm going to continue. I'm going to consider the companion load in a minute. So you recall this one is 1.25 times P of my dead load plus 1.5 times P of my snow loads. This is the axial load, right? And if I do that, I'm going to get 488 kilonewtons. That's a number that you'll recognize from before. This was one of the cases that we checked when we did our very rough calculation at the beginning. Okay, the VF, 1.25 times 2, it's 1.5 times 2.67. Okay, so again, I finished the shear check, and then I'm just looking at the MF at the top for this, because that's where it's going to be the highest in this case. Okay, so since I only have dead and snow, my KD equals 1. Okay, so now I'm going to do the one where I'm going to check the wind load with the lower bound D. Okay, so the D goes down, the dead load pushes down at the top, the wind load pushes up. So that means the wind load is counteracting the dead load. So that means instead of factoring my dead load up, I'm going to try to factor it down in case the wind load is going to govern. Like if the upward wind load governs in this load case, then I'm not going to want to be factoring the dead load up because it's going to help me. Right, so this is the one I'm going to call load case 3B, which is dead load factored down and wind load included as a companion load. So here I have now instead of 1.25 dead, I'm doing 0.9 times P dead plus still 1.5 times P snow, and this time plus 0.4 times P wind load, and this one happens to be negative because it's pointing upwards. And if I calculate that, I get 395 kilonewtons, and it is down. So there is no uplift in this particular load case. Okay, so let's do the shear. One thing I didn't mention here is that the shear, well, you know what I'm going to do? I'm going to consider them all to be positive because we have a negative shear and a positive shear from the beam. So I'm going to consider them all to be in the same direction. Okay, that will be a conservative approach. Like you'll see, you know, we only have shears in one direction from the axial loads, but we have both directions of shear in the, well, we have a shear going in this direction and we have a shear going in that direction. So I'm going to just add up the absolute value of all of those. So instead of taking the negative here, okay, so I'm also doing now this time the moment at the top and at 1 meter down. Since now I have the wind and the wind is maximum 1 meter down, so I'm going to check both of these and see which one governs. And if I do this one, I'm going to get negative 1.46 kilonewton meters. So out of these ones, this one is going to govern. Okay, so that's the maximum moment for load case 3B. Okay, now since this one includes wind load, then the KD is not 1.0 anymore, it's 1.15. Okay, I'm going to continue and do load case 3C. Guess on the next page. Now this time, I'm going to do basically the same thing, except I'm going to try it. Since there was no uplift on the wind, I'm going to do this load case now with the 1.25 dead, because it turns out that the dead load is actually going to hurt us instead of help us for this load case for the purposes of axial load. So this is basically the same thing as load case 3B, but with 1.25 dead instead of 0.9. Okay, so now I have a governing moment. Happens to be at the top for load case 3C. Very good. I calculated the shear and the axial load. And now we're going to move to load case 4A. And we're going to do 4 of these. So maybe what I'm going to do is just explain my approach, and then I'm just going to write them all out. So coming back to this table. Okay, for 4, we have 1.25 dead, or 0.9 times plus 1.4 wind. And remember, wind is an uplift. So this is the case where we're most likely to get a uplift force. And then we have companion load, live, or snow. We don't have live, so we just have snow. So the four load cases that I'm going to check for this are just 0.9 dead and 1.4 wind. That's the first one, right? Second one is going to be 1.25 dead and 1.4 wind. Okay. Then I'm going to do those two same with the companion load. So I'm going to come up with 4 different types of load cases for load case 4. So I'm just gonna write them out instead of explaining as I go. Okay, so for the first one, I do my PF calculation, and actually it's going to be PF or TF because I do 0.9 dead plus 1.4 wind. The wind in this case is negative, right? It's negative 100 kilonewtons in the upwards direction. So when I do that and I factor the dead load down and I factor the wind load up, so factor dead load down by 0.9 and wind load up by 1.4, I actually do get a tension force. So this is not a PF anymore. This is a TF. So our member is acting as a tension member effectively for this load case. So that's a slight uplift. Now this is the same load case, except now the dead load is acting down, is having the full 1.25. So now we get no uplift. Okay, so there are the numbers for load case number 4B. So 4C is going to be the same one, but this time with the added companion load of snow. So the same one, but with 1.25 instead of 0.9, and this is finally the last one. So we can see that basically always the moment at 1 meter down was the one that governed. So that's fine. So, you know, we could have saved a little bit of effort. Well, except for, oh, that's not true. So in a few load cases, the ones at the top govern. So, but for all the load case 4s, it was the second one that governed. Okay, so we needed both. So now what I'm going to do is I'm going to take all of these and I am going to summarize them all in a table so that we can see them all together. Oh, one thing I forgot was to just put the KDs on all of these that I missed. So 3B was 1.15 because it had wind. 3C also has wind, so KD equals 1.15. 4A has wind. In fact, all the rest of these have wind because these are the wind load cases for 4. Okay, so they were all 1.15. I'm going to include that in the table. So now back to putting the table together. Okay, so now we have them all laid out. This is just all of the data that we just compiled, but put all together in one table. Now we can take a look at these and see if there are any that we can kind of figure out which ones are going to govern and maybe if some we need to let go of. Okay, well, for KD equals 1.0, there's only one case. So that means that these ones is going to be a combination that we're going to for sure have to check. The same for 1.0. That's the governing one for 1.0 KD because it's the only one for 1.0 KD. Okay, so these ones we're both going to have to check. And check. Okay, this one here, number 3B, is basically never going to govern. So this one, because it is lower in all cases than 3C, so will never govern. Okay, and now, like if I try to pick out some of the maximum values here, this is the maximum value of the axial load that we're going to see. This is the maximum value of the negative axial load, so the tension that we're going to see. And this is the maximum value of the moment that we're going to see. And down here, this is the maximum value actually of the shear that we're going to see. So, you know, 448 and 17.9, like if we look at these, this is the highest, oops. You know, this is the highest moment, this is the highest axial load in compression, but it is not the highest moment, right? So, you know, is that going to govern? Or maybe is something like this going to govern instead, which has also kind of a high, definitely not as high PF, but it has a much higher MF, right? So which one of these is going to govern? You know, like probably 4B is not going to govern, but 4C is probably not going to govern either. But so it's probably going to be between 3C, you know, when we're looking at the beam column interaction. You know, I can either have take up more of the axial load and less of the moment, or maybe I have another case where I'm taking up more of the moment capacity and less of the axial load capacity, right? So on the balance, which one of those is going to govern? We're basically going to have to check them. Okay, so for the interactions, we're going to have to check the rest of these. And certainly 4A we're going to have to check because that's the only tension and bending interaction. And it also has the highest amount of bending. We're really not sure about which one of these interactions is going to govern. Just a few minor corrections to the shear values. So I'm going to put a cut in this video now, and in the next video we're going to look at deflections, criteria for this beam, and choosing a trial section to move forward with for the full design.